NanoHub U, online instruction.
Welcome back to Unit 4 of our course on quantum transport, and this is the 7th lecture. Now, as you know, in this unit, we have been illustrating the use of this NEGF method, which we developed in earlier units, using examples from spin transport. And the spin transport involves, usually the physics involves magnetic contacts or special properties of the channel like spin-orbit coupling. And we have talked about how to include these into the description of this H and the gammas or sigmas that describe the contacts. And one key point, as I mentioned, is when you include spin, you have twice as many basis functions because every upspin basis has a corresponding downspin basis. And so compared to the spinless description, you have matrices which are twice as big, like 5 by 5 becomes 10 by 10. Now, in this lecture, what we'll focus on is about the interpretation of the quantities that you can calculate from NEGFs, specifically this Gn. That is, given H and sigma or gamma, you can calculate current, you can calculate electron density, density of states, any quantity of interest. And what we'll talk about here is how you interpret that. And specifically, we focus on this quantity. And what we'll show is that supposing we look at one point, which means two basis functions, then the Gn we'll get will be a 2 by 2 matrix. And what we'll show is that the elements of this matrix gives you the number of electrons, n, but it also tells you the spin, the average spin, the net spin of the electrons. And spin is like points in some direction. It has a z component and an x component and a y component. And what we'll talk about is why the Gn looks like this and how you can extract this information from Gn. Okay. Now, just to remind you, as we had discussed earlier, if you have a spin pointing in the n direction, in this direction described by the vector n, then if you thought of it as a vector, its x, y, and z components would be given by this cosine theta, sine phi, sine theta, cosine phi. That's what you learn in vector algebra. With spins, it has these two complex components, which are denoted by C and S, where C is defined as given here and S is defined as given here. Now, consider an electron in a state pointing along n so that its components are given as C and S. What is the corresponding Gn? That's this psi dagger. So the principle is simple. You take Cs multiplied by C star S star. And if you write it out, you'll get this 2 by 2 matrix. You see, this is 2 by 1, this is 1 by 2, so when you multiply, you get 2 by 2. And these individual elements then, you can do the multiplication and write it out. You'll get cosine square half theta, cosine half theta, sine half theta, and there'll be a phase factor because of this, and same here, and so on. Next, what we could do is use these trig identities, thing which you have used before, so you're probably getting used to it now. So write this cosine square half theta as half of 1 plus cosine theta, or sine square half theta as half of 1 minus cosine theta. And this quantity is half of sine theta, and same here. Now you'll notice that the elements that appear here, they are actually like the components of the corresponding vector. So for example, this cosine theta is actually the z component of n. So you can write it as 1 plus nz. Similarly, the real part of this is sine theta cosine phi. That's like the x component of n. The imaginary part is sine theta sine phi. That's like the y component of n. So you can write these in terms of the components of that vector n. And this you could write it out in terms of our favorite 2 by 2 matrices, namely the identity matrix, the Z component of the Pauli spin matrix, and then the X component of the and Y component of the Pauli spin matrices. This and this together give me 1 plus Nz and 1 minus Nz. That's the diagonal part. These two give me the off-diagonal part, Nx minusIny and Nx plusIny. So what you have then is I plus Nz sigma Z plus Nx sigma X plus Ny sigma Y. So you could write it compactly as half of I plus sigma dot N. Okay. Now, let's look at a couple of examples to see, to make sure we understand this. So for example, if you have a state that is pointing along the plus Z direction, so we'll confine ourselves to states in the Zx plane so that we can take the phi to be 0. So there is no phase factor here. That's 0, so that drops out. So if theta is 0, that's in the Z direction. So you get cosine 0, that's 1, sine 0, that's 0. So the wave function is like 1, 0. That's a spin pointing in the Z direction. So when you take Gn, that's like psi dagger. So 1, 0 times 1, 0. That gives you 1, 0, 0, 0. Now consider something along the negative Z direction. And you can show in that case the wave function would be like 0, 1, 0, 1. So when you multiply it out, you'd get 0, 0, 0, 1. So that's a spin in the negative Z direction. Now what about a spin that points along the X direction? Okay, then you can show that your wave function would be something like 1 over square root of 2, 1, 1. Why is that? Well, phi is 0, but now theta is 90 degrees. So this is like cosine 45, which is 1 over root 2. This is sine 45, 1 over root 2. So that's the wave function. And so you have to multiply it by the psi dagger. So the dagger is 1, 1. And of course, you still have the divided by square root of 2. So when you multiply it out, you get half 1, 1, 1, 1. So in this case, you see, you have both diagonal elements are 1, 1. That kind of suggests that as if, this was an upspin electron. So this was 1, rest is 0. This is downspin, this is 1, rest is 0. And the X spin pointing along X is like a little bit of plus Z and a little bit of minus Z. And so that's why it's like half here and half here. But it goes more than that. You'll notice I also have an off-diagonal element. Now, to appreciate this subtle point, consider what you mean by unpolarized electrons. That is, normally you see you have equal numbers of up and down. That's what you might call unpolarized electrons. Now, if you had unpolarized electrons, then the corresponding Gn would be like 50% of this plus 50% of that. And that would look something like this. You see, this is 1, or rest 0, this is zeros, that's 1. So if you take 50% of this and add 50% of that, you get this. So that's the Gn corresponding to unpolarized electrons. And here it's hard to write down a wave function, you see, because if you say, well, unpolarized electrons are like equal amounts of plus Z and minus Z, and so I'll write the wave function like this. Well, that would imply a Gn of something looking like that. And that would actually physically not represent unpolarized electrons. It would represent X-polarized electrons. So there is a big difference. You see, X is equal amounts of plus Z and minus Z. But unpolarized means, I guess, incoherent mixture of is 50% of this and 50% of that. The difference is, you see, if I put a analyzer in the plus Z direction, so if you had unpolarized light, 50% of, not light, I guess, electrons, 50% would get through. If you had, similarly, if you looked at minus Z, another 50% would get through. The same with plus X. But in this case, if you put an analyzer in the X direction, even then, actually, only 50% would get through. What you can show is this is 50% plus z, 50% minus z, but it's also 50% plus x, 50% minus x. Those are all basically same thing. On the other hand, here, if you put an analyzer in the x direction, 100% would get through. This may not be obvious from just what we discussed, but the important point I'm trying to make is these off-diagonal elements are extremely important. And if you leave out the off-diagonal, what you get is this random mixture of plus z and minus z. Whereas it's this one that shows you it's not a random mixture, it's a coherent superposition of plus z and minus z. Now, this is how you'd interpret the wave function or the Gn for a single electron. If you have lots of electrons, then you can just add them all up. So instead of I plus sigma dot n, you'd have Ni plus sigma dot s, where n is the total number of electrons and s is the total spin. So the idea is that for single electron, you interpret these in terms of probability, that you have got an electron. If I measure the spin in a certain direction, what is the probability that the answer will be positive, that I get a spin in that direction? Whereas, so that's, let's say, 50-50. But if I have millions of electrons, what it means is 500,000 are up, 500,000 are down. Okay. So, but a lot of these subtleties are involved in this off-diagonal elements, which tell you this Sx minus Isy part of it. Now, next point is, given that Gn, let's say, looks like this, how would you extract the information we want? Because this is a 2 by 2 complex matrix. What I can relate to easily is things like n and s. That is, what is the number of electrons? What is the total amount of spin? So, given this matrix, how will I extract those quantities? So, mathematically, there's a formal way of doing this. Of course, you could look in here and say, okay, this is n plus sc, this is n minus sc. So, I'll add these two up, and that should give me n, because the sc will cancel. And formally, you could say, oh, what you should do is take the trace of Gn. Trace means add up the diagonal elements. So, you can see if you add it up, you get n. Actually, there's a more formal way of seeing that, and that is, you see, you note that you can write this as Ni plus sigma x Sx, sigma y Sy plus sigma z Sc. Now, when I take a trace of this matrix, you'll notice that all the three Pauli matrices have zero trace. You see, if you add up the diagonal elements, it's 0. Add up the diagonal, that's 0. Add up the diagonal here, that's also 0. And the only one which doesn't have a 0 trace is the identity matrix. There the trace is 2. So when I take the trace of this, trace of I gives me 2, which cancels the half, and I get n. And the rest don't give me anything. See? So in this case, as I said, you could have seen it from here right away, but this formal thing actually helps you also see how you could extract information about Sx, for example. So supposing I want to know what is the spin in the x direction. What I could do is multiply Gn by sigma x. So what would happen is I'm multiplying from the right with sigma x. So you get sigma x times I, that's sigma x. Here I get sigma x times sigma x, which is sigma x squared. And the thing is, sigma x squared is actually I. And this you can see from this general relation that I had stated earlier. You know, that is obeyed by for any arbitrary vectors v1 and v2. So if we choose v1 and v2 to be the unit vectors in the x direction, then you see this becomes sigma x, that's also sigma x, so you get sigma x squared. X cross x is 0, so that drops out. X dot x is 1, so you get I. Okay? So you can show that sigma x squared equals I. Another thing you could check out is that if you have sigma y times sigma x, which means we choose this to be the y vector, unit vector along y, this is the unit vector along x, then y dot x, that drops out. Y cross x, that's minus z, and so this becomes minus I sigma z. And if you to look at sigma z sigma x, that would be like putting a unit z vector here, unit x vector there, and then you'll get plus I sigma y. And that's what I've used here. You see, I'm multiplying by sigma x, so I got sigma x square, that's I, sigma y sigma x, that's minus I sigma z, and then sigma z sigma x, that's plus I sigma y. So when I multiply by sigma x, we get this. Now, how does that help us? Well, now you see if I take the trace, I only get Sx. Why? Because all these other sigmas have zero trace. And the trace of I is 2, which cancels the half, and so you get Sx. So you get that. And what you can show is, the same works for the other components also. You multiply by sigma y, trace it, you'll get Sy. Multiply by sigma z, trace it, you'll get Sc. So in general, you can multiply by sigma in any particular direction I and trace it, and you'll get the spin in that direction. And in general, if you want to write the spin in a particular direction n, some special vector n, that's like you have to take s dot n. So what you should do is multiply gn over 2 pi with sigma dot n. And then take the trace. So if n is x, you multiply by sigma x. N is y, you multiply by sigma y, and so on. So this would be the general way then of finding the spin in any particular direction once you have calculated the Gn. Now, just to connect up with what you normally learn in quantum mechanics, I'd like to point out that you could actually interpret this as the spin operator. That is, you see, Gn over 2 pi is like psi dagger, as we discussed before. And when you're taking trace, you can move these things around cyclically. Namely, trace of ABC is the same as trace of, you see, BCA. As long as you move it in the right order, you're fine. So here also what we can do is, I can take the psi from here and move it to the end. And then you can see what we are taking is the trace of psi dagger, this quantity, and psi. And that's the usual prescription you learn in quantum mechanics. That given certain wave function, the way you find the expectation value of some quantity, which is represented by an operator, is by taking this trace of psi dagger, the operator, times psi. So this you could interpret as this spin operator in the direction n. Okay. Now, this is for if you wanted the spin or the number, if you wanted the number of electrons, of course, you just take the trace of Gn. And you have the number, and if you want the spin, you do this. Similarly, you could calculate currents if you wanted. That is, earlier we talked about the current operator. If you multiply by sigma dot n, trace it, then you'll get the spin current in a particular direction. And the spin current is a vector. And note that it's I guess current is a vector usually because of it can have a direction. But here we are talking about current in a particular direction. And it's still a vector because it could be carrying a spin in a particular direction. So what I mean is we're all talking about current in this direction, and this vector represents the direction of the spin that is being carried, right? Not the direction in which the current is flowing. So that's this vector. Now, here we said that this is a 2 by 2 matrix. If you look at this one point, in general, a device might have many more points. You know, I've shown 3 here. It might have 20 points or so. But then the way you should look at it is, if you looked at the Gn matrix here, it would be like a 6 by 6. But what you're looking at is the diagonal blocks. So this first block tells you the n and s here at this point. N2, S2 tell you what it is here. N3, S3 tells you what it is there, and so on. So you can calculate it anywhere inside your device. So what we'll do next is, so what we have talked about is how from the Gn you can get this n and s at a particular point in your device. And what we'll talk about next is how that then translates into this concept of voltages or the electrochemical potential, the usual potential and the spin potential or the spin voltage. That's what we'll do in the next lecture. Thank you.